Freeze on these images, grainy, pixelated, easy to dismiss. But this is where the story begins. A man in his backyard pointing an 8-inch telescope at the night sky and capturing something the professionals didn't expect. 3i Atlas, the third known interstellar visitor, except it refuses to play by comet rules. No tail, odd shape, a cosmic smear that shouldn't exist. And when ESA's orbiter over Mars looked closer, it confirmed what Tiago saw. Same shape, same absence. That's when whispers began. Is this really natural? Or engineered? Tonight we trace the coincidences stacking too neatly to ignore. Stay with me, because what starts as pixels might end as paradigm shift. Part 1. Hook. Breaking news. You're looking at 2 images right now, and one of them is about to ruin your week. The first one was taken by an amateur astronomer named Tiago in his backyard in late September 2024, using an 8-inch telescope you could buy for less than a used car. The second one was captured by the European Space Agency's Mars orbiter in early October, a machine worth more than your neighbourhood, floating in space, bristling with instruments that can spot a coffee cup on the Martian surface. They're both pointed at the same thing, an object called 3i Atlas, supposedly a comet passing through our solar system from somewhere beyond the outer edges of the Oort cloud. Here's the problem. When a backyard telescope and a €1 billion spacecraft show you the same weird blob, and that blob looks nothing like what it's supposed to be, we need to talk. Comets are supposed to have tails. That's literally the defining feature. The word comet comes from the Greek word for hair, because these things are meant to stream across the sky like someone dragged a brush through wet paint. When a comet gets close to the sun, the ice sublimates, gas and dust explode outward, and you get that glorious tail stretching millions of miles behind it. The coma, that fuzzy cloud around the nucleus, should be round, or at least diffuse. That's Astronomy 101. That's what every telescope operator from Galileo to your nephew with a toy refractor expects to see. But neither of these images shows that. Not Tiago's pixelated capture, not ESA's high-resolution frames. What they show instead is something elongated, something dense, something that looks more like a blurred cigarette or a metallic shard than anything with a tail. The shape is consistent across both observations, across 2 completely different instruments, across 2 different vantage points separated by tens of millions of miles. That's not supposed to happen. Let me introduce you to Tiago, who goes by Dobsonian Power on social media. He's not some conspiracy theorist filming blurry lights through his bathroom window. He's been doing serious amateur astronomy for years, documenting captures transparently, sharing his raw data, walking people through his process. He uses an 8-inch Dobsonian telescope, a classic design loved by amateurs because it's simple, sturdy, and packs serious light-gathering power. His camera is a TubeTech 24AC, a solid choice for planetary and deep sky imaging. This is the kind of setup thousands of hobbyists use. There's nothing magical about it. What's magical is what he caught on September 28, 2024, when he aimed that telescope at 3i Atlas and stacked his exposures into a single image. He posted it online almost immediately. No fanfare, no breathless claims. Just, here's what I saw. Then the European Space Agency released their images on October 11th, almost 2 weeks later. Their official statement was careful, clinical, the way space agencies always are when they're trying not to start a panic. They confirmed a bright coma, sure, but noted the absence of any long tail. That's astronomer speak for, yeah, this thing is weird. The Mars Express orbiter and the Trace Gas orbiter both captured the object using CASIS, the Colour and Stereo Surface Imaging System, one of the most advanced imaging tools we have floating around another planet. These aren't grainy webcam shots. These are calibrated, multi-filter exposures taken from instruments designed to resolve surface features on Mars. And what they saw matches what Tiago saw. A bright, elongated blob with no tail. No streaming gases, no diffuse coma. Just that same stubborn, cigar-like shape. Here's where the story gets interesting. Major outlets picked up on Tiago's images before ESA even released theirs. Motor Biscuit, a site that usually covers cars and motorsports, ran a piece on the amateur astronomer who might have captured something extraordinary. That's the kind of crossover coverage that signals a story breaking out of niche astronomy circles and into the mainstream. Social media exploded. Thousands of people engaged with Tiago's posts, downloading his raw frames, analysing them, trying to find the trick. And here's the thing, they couldn't. Skeptics tried to debunk it. They looked for motion blur, camera artifacts, atmospheric distortion. None of it held up. The object persists across multiple frames. Its shape is consistent. It's not a smear from a fast-moving point source. It's not a lens flare. It's something real, captured by Tiago's telescope, and then confirmed by ESA's instruments 2 weeks later from a completely different angle. So if Tiago was first, and ESA confirmed him, what else might he have caught before the professionals are willing to admit it? That's the question gnawing at the back of my mind as I write this. Because timing matters in science. Credibility is built on independent verification, and when an amateur beats a space agency to the punch, and the space agency quietly validates the amateur's findings without much fanfare, you start to wonder what conversations are happening behind closed doors. You start to wonder if there's a reason the language in ESA's release was so restrained, so careful not to speculate. The tension between official caution and amateur boldness is palpable. Tiago can say, "This looks alien." He can post it on social media and let the internet run wild. ESA can't. They have reputations, funding, international partnerships. They have to be careful. But careful can start to look like evasive when the data keeps piling up. We're used to a world where professionals lead and amateurs follow, where NASA makes the announcements and hobbyists marvel from the sidelines. But astronomy has always been different. Amateurs have discovered comets, spotted supernovae, tracked asteroids that professionals missed. The tools are cheap enough now that anyone with patience and a decent telescope can contribute real data. Tiago's images aren't just lucky snapshots. They're part of a growing ecosystem where citizen scientists can force the conversation, can put evidence on the table that institutions can't ignore. And when that evidence suggests something doesn't fit the model, when it suggests we might be looking at something we don't understand, the implications spiral outward fast. Because if this isn't behaving like a comet, if every attempt to explain it away as normal cometary activity keeps running into problems, then we have to start asking uncomfortable questions. What is it? Where did it come from? And why does it look so wrong? Hold that thought. Because before we dive into the rabbit hole of exotic explanations, we need to understand exactly how Tiago got that shot, and why every attempt to dismiss it has failed. Part 2. The image that started the frenzy. Tiago's setup is straightforward, almost humble. An 8-inch Dobsonian telescope is what serious amateurs cut their teeth on. It's a Newtonian reflector on a simple altazimuth mount, meaning it can swing up, down and left-right but doesn't track the sky automatically like fancier equatorial mounts. You have to nudge it along as the Earth rotates, keeping your target centered in the eyepiece. It's hands-on astronomy, the kind that requires patience and practice. The ToupTech 24AC camera he uses is a colour CMOS sensor, sensitive enough to capture faint deep sky objects, but not so expensive that you need a grant to afford one. You attach it where the eyepiece would go, connect it to a laptop and start recording frames. Astrophotography isn't like snapping a picture with your phone. You're not taking one photo. You're recording dozens, sometimes hundreds of frames, and then stacking them together using software that aligns the images and averages out the noise. This technique, called lucky imaging or frame stacking, is how amateurs pull detail out of faint, distant objects. Tiago recorded multiple exposures of 3i Atlas over the course of the evening on September 28, 2024. Each frame captured a slightly different moment as the object moved against the background stars. Then he used stacking software to align those frames and combine them into a single image. The result was striking, and I mean that in the most unsettling way possible. What emerged from the stacked frames wasn't the soft, fuzzy glow of a comet's coma. It was something dense, something with structure, something elongated like a shard of metal tumbling through space. The shape was visible even in the unstacked frames, which is important because it rules out stacking artifacts. If the elongation only appeared after processing, you could argue it was a software glitch. But it's there in the raw data, frame after frame, the same weird geometry. A skeptic, someone who downloaded Tiago's raw files and tried to debunk the whole thing, spent hours running their own analysis. They adjusted the contrast, tweaked the alignment, tried different stacking algorithms. They were looking for the flaw, the mistake, the mundane explanation, and they found the same shape Tiago did. That's the moment the story shifted from interesting to uncomfortable. Because when someone actively trying to disprove your findings ends up confirming them, you're no longer dealing with observer bias. You're dealing with something real in the data. The skeptic posted their results online, admitting they couldn't explain it away. That post went viral too. The conversation was no longer about whether Tiago's image was legitimate. It was about what the hell that thing actually was. Let's talk about the criticisms, because they're important. The first one you'll hear is motion blur. 3i Atlas is moving relative to Earth, and if your exposure is too long, a point source like a star or asteroid will smear into a line. Could that explain the elongated shape? No, and here's why. Motion blur creates a specific kind of smear that follows the direction of motion. It's uniform, predictable, and affects all objects in the frame the same way. Background stars in Tiago's images show normal point spread functions. They're round, sharp, exactly what you'd expect. If motion blur were stretching 3i Atlas into a cigar shape, it should be stretching the stars too. It's not. The object's elongation doesn't match the motion vector you'd calculate from its known trajectory. It's oriented wrong. The shape persists even in shorter exposures where blur should be minimal. Motion blur is a non-starter. Camera artifacts are the next go-to explanation. Maybe the sensor has a defect, or there's dust on the optics, or the image has been over-sharpened in processing. Tiago addressed this by showing multiple frames with the object in different positions relative to the sensor. If it were a camera artifact, it would stay in the same place on the sensor no matter where the telescope pointed. It doesn't. The object moves with the sky, which means it's out there, not in here. Atmospheric distortion is another favourite. Earth's atmosphere is turbulent, and that turbulence makes stars twinkle and blurs fine detail. Could atmospheric seeing conditions stretch 3i Atlas into an elongated shape? Again, no. Atmospheric distortion is random and time-varying. It causes shimmering and blurring, but it doesn't create the same elongated morphology across dozens of independent frames taken over hours. And critically, it doesn't explain why ESE's Mars orbiters, looking through the vacuum of space with no atmosphere to distort the image, saw the same thing. Tiago described the moment he realized something was off. He'd been tracking 3i Atlas for a while, expecting the usual comet appearance. When the stacked image resolved on his screen, he stared at it for a long time. He told his followers it looked alien, not in the sense of little green men, but in the sense of genuinely foreign, something that didn't belong in the catalogue of normal objects. He didn't jump to conclusions. He shared the data and asked for opinions. That transparency is what built his credibility. Within hours, his post was trending on X, the platform formerly known as Twitter. Screenshots circulated. Astronomers, both amateur and professional, chimed in. Some offered explanations. Others admitted they were stumped. Thousands of people engaged, downloading the files, running their own analyses, debating the implications. This wasn't a fringe claim whispered in conspiracy forums. This was a public, transparent, peer-reviewed by the internet moment. Tiago wasn't seeking fame. He didn't monetize the moment or start a podcast about alien visitors. He kept doing what he always did, documenting the sky, sharing data, engaging with the community. That humility matters. It's easy to dismiss someone who's trying to sell you a story. It's harder to dismiss someone who's just showing you what they saw and inviting you to check their work. The virality of the images wasn't manufactured hype. It was genuine surprise rippling through a community of people who know what comets are supposed to look like. And this didn't look like one, not even close. The more people examined it, the harder it became to explain away. Coincidences started stacking up alongside the image frames. Independent observers in different locations reported similar morphology. The object's brightness didn't fluctuate the way a tumbling nucleus would. The lack of a tail wasn't just an imaging fluke, it was consistent across every observation. But here's the real kicker. Almost 2 weeks after Tiago posted his images, ESA released theirs, and they looked eerily similar. That's not a coincidence you can laugh off. Part 3. The professional confirmation. The European Space Agency's Mars Express and Trace Gas Orbiter aren't your average space probes. Mars Express has been orbiting the red planet since 2003, mapping its surface, studying its atmosphere, searching for water. The Trace Gas Orbiter, or TGO, arrived in 2016 with a mission to sniff out methane and other gases that might hint at biological or geological activity. Both spacecraft carry advanced imaging systems, and one of the most powerful is CASIS, the colour and stereo surface imaging system mounted on TGO. CASIS was designed to image the Martian surface in stunning detail, resolving features smaller than a car from orbit. It's a 4-megapixel camera with multiple color filters capable of producing stereo pairs that reveal topography. When ESA pointed CASIS at 3i Atlas in early October 2024, they weren't using some off-the-shelf consumer camera. They were using a precision scientific instrument. The images came back, were processed, and were released to the public on October 11, 2024. ESA's official statement was measured. They noted a bright coma around the nucleus, which is expected for a comet. Then they added the caveat, "No long tail was observed." That single phrase carries more weight than it might seem. Comets, especially active ones bright enough to image from Mars' orbit, should have visible tails. The gas and dust being blown off by solar radiation pressure should create a streaming tail pointing away from the Sun. 3i Atlas didn't have one. The images showed a compact, bright central region with some diffuse glow, but nothing like the classic tail structure. And critically, the morphology matched what Tiago had captured from Earth. The same elongated, dense appearance, the same lack of streaming material. 2 independent vantage points separated by tens of millions of miles saw the same thing. Why does having 2 vantage points matter so much? Because it rules out a whole class of observational errors. If Tiago's image were a fluke caused by his specific viewing angle, or atmospheric conditions, or equipment quirks, ESA's images from a completely different position in space wouldn't match. The fact that they do means the object's appearance isn't an artifact of observation. It's intrinsic to the object itself. Mars Express and TGO were looking at 3i Atlas from a perspective Earth-based observers can't access. They were closer in some orbital configurations, farther in others. The geometry changes, the lighting changes, the background changes, but the object's weird morphology persists. That's consistency, and consistency is what separates signal from noise in science. ESA's imaging process is rigorous. They don't just point a camera and snap a photo. CASIS takes long exposures through different color filters, capturing red, blue, green, and infrared wavelengths. These images are then calibrated using flat fields and dark frames to remove sensor artifacts. Geometric distortions are corrected. Stars are used as reference points to anchor the astrometry. The data pipeline is designed to produce scientifically valid images that can be analyzed for composition, albedo, motion, and structure. When that pipeline spits out images of 3i Atlas showing a bright blob with no tail, that's not a glitch. That's what the object looks like. ESA even produced a GIF animating the object's motion against the background stars, making its trajectory clear. And in every frame of that animation, the morphology holds. No tail, no diffuse coma spreading outward, just that stubborn, enigmatic shape. The timeline is crucial. Tiago captured his images on September 28, 2024. ESA's observations happened in early October, with the public release on October 11th. That's nearly 2 weeks between Tiago's post and ESA's confirmation. During that time, Tiago's images were circulating, being analysed, being debated. When ESA's images came out and matched, it wasn't just validation, it was amplification. The mainstream media, which had been cautiously covering Tiago's discovery, suddenly had official confirmation from a space agency. Articles started appearing in science outlets, tech blogs, even general news sites. The Guardian ran a piece noting the anomalies but downplaying the extraterrestrial angle. Motor Biscuit updated their coverage. Social media lit up again. The story wasn't dying down, it was gaining momentum. Independent, time-separated confirmations reduce the chance of error. That's a bedrock principle of science. One observation can be a mistake. 2 observations from different instruments, different locations, different times, start to look like a pattern. 3i Atlas wasn't caught in a single fleeting moment by one lucky amateur. It was documented repeatedly by ground-based telescopes and space-based imagers over days and weeks. Each observation added another layer of credibility. Each failure to find a tail, to see normal cometary activity, deepened the mystery. ESA's caution in their language, their refusal to speculate about what this means, almost makes the anomaly worse. Because they're not saying it's nothing. They're just saying it's not what we expected, and when a space agency tells you something isn't what they expected, you should pay attention. But if ESA's images lock in the weirdness, they also raise the stakes, because now we're not just talking about one amateur's controversial capture, we're talking about a confirmed anomaly observed by some of the best instruments humanity has floating in space, and that brings us to someone who's made a career out of taking anomalies seriously. Part 4. Avi Loeb's Alarm Bells. Avi Loeb is not a fringe figure. He's a tenured professor at Harvard, former chair of the astronomy department, and one of the most published theoretical astrophysicists of his generation. He's also the guy who looked at Oumuamua, the first confirmed interstellar object to pass through our solar system, and said, maybe that's not a rock, maybe that's a piece of alien technology. That suggestion, articulated in his book Extraterrestrial, and in dozens of papers and interviews, made him controversial. Mainstream astronomers accused him of chasing headlines, of lowering scientific standards, of giving credibility to wild speculation. Loeb's response was simple. Anomalies deserve scrutiny. If something doesn't fit the model, you don't ignore it. You investigate. And if the investigation leads you somewhere uncomfortable, that's where science gets interesting. Oumuamua arrived in 2017, tumbling through the inner solar system on a trajectory that confirmed it came from interstellar space. It was elongated, possibly 10 times longer than it was wide, which is unusual but not impossible for an asteroid or comet. Then things got weird. As Oumuamua sped away from the Sun, it accelerated slightly, as if being pushed by an unseen force. Comets do this because outgassing creates thrust. But Oumuamua didn't have a visible coma or tail. No gas, no dust, no cometary activity. So what was pushing it? Loeb proposed that the acceleration was consistent with a light sail, a thin reflective structure that uses solar radiation pressure to propel itself. He argued that Oumuamua's shape, its brightness variations and its acceleration profile, matched what you'd expect from artificial technology better than any natural explanation. The astronomy community pushed back hard. They proposed exotic natural mechanisms, hydrogen icebergs, nitrogen snowflakes, dust bunnies held together by who knows what. Anything to avoid the alien hypothesis. 3I Atlas isn't identical to Oumuamua, but the parallels are hard to ignore. Both are objects on interstellar or highly unusual orbits. Both show morphologies that don't match expectations. Both lack obvious cometary tails despite being bright enough to observe. Loeb has commented publicly on 3I Atlas, noting the trajectory anomalies and the odd appearance in both amateur and professional images. He's careful not to jump straight to aliens. His argument is subtler. He says, this object is exhibiting behaviours we don't fully understand. We should investigate it with every tool we have. Spectroscopy, radar, continuous imaging, multi-wavelength observations. We should treat it as a scientific puzzle, not dismiss it because the implications are uncomfortable. That's the fight Loeb is waging, not a crusade to prove aliens exist, but a battle against premature dismissal. The inclination anomaly is one of the things that bothers him. Comets that originate in our solar system tend to have orbits that cluster around the ecliptic plane, the flat disk where planets orbit. Interstellar objects can come from any direction, but their trajectories should still follow the laws of physics. 3I Atlas has an orbital inclination that doesn't neatly fit either category. It's not aligned with known comet families. It's not following the trajectory you'd expect from something randomly wandering in from the galaxy. Loeb argues that these kinds of statistical anomalies, when combined with morphological oddness, should trigger investigation, not hand-waving. The mainstream response has been to label 3I Atlas a comet and move on. Loeb asks, based on what evidence? Based on the lack of evidence that it's anything else. That's circular reasoning. That's what happens when the default assumption is so strong that anomalies get explained away instead of explained. Critics accuse Loeb of chasing media attention, of diluting science with speculation. He gives interviews, writes op-eds, appears on podcasts. He's unapologetic about it. His philosophy is that science should be open, public, and willing to ask uncomfortable questions. He points out that the history of astronomy is full of discoveries that sounded ridiculous before they were proven. Exoplanets, black holes, dark energy, all of these things were once fringe ideas. The difference between fringe and mainstream is data. If the data supports something strange, you follow the data. If the data keeps accumulating and the anomalies keep stacking up, you don't bury your head in the sand, you sound the alarm. That's what Loeb is doing with 3I Atlas. He's not claiming it's alien, he's saying, this deserves a closer look. and the fact that his voice is one of the few in the professional community willing to say that out loud tells you something about the state of modern astronomy. The intellectual tension is real. On one side, you have astronomers who've spent their careers studying comets, who have models and simulations and decades of observations telling them what comets should look like. When something doesn't fit, their instinct is to tweak the model, to find the natural explanation, to avoid the extraordinary claim. On the other side, you have people like Loeb saying, what if the models are incomplete? What if the universe is weirder than we've allowed ourselves to imagine? And caught in the middle are the images. Tiago's backyard capture, ESA's billion-dollar confirmation, the absence of a tail, the presence of something that shouldn't be there. The question isn't whether Loeb is right. The question is whether we're brave enough to find out. Because this isn't just another viral UFO sighting. This is different, and that difference matters. Part 5. Why this isn't just another viral sighting. Every few months, the internet goes wild over some grainy video of lights in the sky. Someone sees a blurry dot moving against the clouds and declares it a UFO. Social media amplifies it. News outlets pick it up. Skeptics debunk it within hours. It's Venus. It's a satellite. It's a drone with LEDs. It's never aliens. The cycle is so predictable that serious scientists tune it out. They've learned to ignore the noise because the signal-to-noise ratio in viral sightings is abysmal. So why should 3i Atlas be any different? Why should anyone care about one more weird thing in the sky? Because this time, the data are real. This time, the observations are scientific grade. This time, the coincidences are stacking up so high that ignoring them starts to feel willful. Let's run through the checklist. First, independent observers. Tiago isn't the only person who's imaged 3i Atlas. Other amateur astronomers around the world have pointed their telescopes at it and reported similar findings. Not identical, because equipment and conditions vary, but consistent in the key anomaly. No tail. Multiple people, multiple locations, multiple instruments. That's not group hallucination, that's data. Second, Earth-based versus space-based. Tiago's images were taken from the ground, looking up through Earth's atmosphere. ESA's images were taken from orbit, around Mars looking through the vacuum of space. Completely different observational contexts, same result. That rules out a huge category of errors related to atmospheric distortion, light pollution, or ground-based artifacts. Third, amateurs plus professionals agree. This isn't a case of hobbyists seeing things that experts dismiss. ESA confirmed the anomaly in their own data. They might not be shouting about it, but they documented it. They published it. The agreement crosses the amateur-professional divide. Fourth, different instruments, same shape. Tiago used an 8-inch Dobsonian and a CMOS camera. ESA used CAS's, a multi-million-dollar space telescope. These instruments have completely different designs, optical paths, sensors, and data processing pipelines. The fact that they both show an elongated, tailless object means the morphology isn't an artifact of any one system. It's real. Fifth, repeated anomaly. The lack of a tail isn't a one-off observation. It's consistent across every image taken over weeks. Comets can have moments where the tail is faint or pointing in an unexpected direction, but this is sustained absence. This is every observation showing the same problem. When you line up these 5 points, the picture gets uncomfortable. This isn't a viral sighting where one person with a blurry iPhone video makes a wild claim. This is a scientific observation that keeps getting confirmed. Compare this to past viral sightings. Someone films a tic-tac-shaped object over the ocean. Turns out it's a distant aircraft, perspective and parallax playing tricks. Someone photographs a triangular craft hovering silently. Turns out it's a kite with LEDs, or a hoax. Someone sees lights moving in formation. Turns out it's Starlink satellites, dozens of them strung out in a line catching the sunlight. Every time the mundane explanation emerges once someone does the math. 3i Atlas isn't like that. The math has been done, the observations have been verified, the mundane explanations keep failing. Motion blur doesn't work, atmospheric distortion doesn't work, camera artifacts don't work. Unusual comet physics might work, but each proposed mechanism has holes, which we'll dig into later. For now, the point is this. The data are time-stamped, raw, and scientific grade. They're not fuzzy lights in the sky. They're calibrated images from instruments designed to do exactly this kind of work. Coincidences happen. Of course they do. You look at enough objects in space, some of them are going to look weird. But coincidences don't stack infinitely. When one thing is odd, you shrug. When two things are odd, you raise an eyebrow. When 3, 4, 5 things are all odd in the same direction, you start asking questions. 3i Atlas has a weird orbit. It has a weird shape. It has no tail when it should. It's been confirmed by independent observers. It looks the same from Earth and Mars. Each of these facts alone might be dismissible. Together, they form a pattern. Patterns are what scientists live for. Patterns are how discoveries get made. And this pattern is screaming that something here doesn't fit. So if this isn't a comet in the normal sense, what is it? That's the question that should be keeping astronomers up at night. That's the question that should be driving a coordinated international observation campaign. Because if we're wrong, if this turns out to be some exotic but natural cometary phenomenon, we'll learn something new about how ice and rock behave in space. And if we're right, if this is something stranger, something that doesn't belong in our catalogue of solar system objects, then we're staring at the biggest discovery in human history. Either way, the answer matters. Either way, we can't afford to shrug this off as just another viral sighting. Because this time, the evidence is too good to ignore. This time, the coincidences are piling too high. This time we might actually need to sound the alarm. And sounding the alarm means understanding what we're looking at, pixel by pixel, hypothesis by hypothesis, until we know the truth. Part 6. Image Forensics. Passing Pixels versus Physics. Astronomy is built on light. Everything we know about the universe beyond Earth comes from photons that travelled across space and hit a detector. A camera sensor, a photographic plate, the retina of your eye. Light carries information. Brightness, colour, direction, how it changes over time. But light can also lie. It can be distorted by the atmosphere, by the instrument, by the processing pipeline. That's why image forensics matter. That's why we have to scrutinise every pixel, every assumption, every claim that something in an image is real versus artifact. When Tiago posted his images of 3i Atlas, the forensic work began immediately. Not just by Tiago, but by hundreds of people who downloaded the raw frames and tried to figure out, is this real or is this an illusion? Let's start with the basics. The point spread function, or PSF, is the shape a point source of light makes when it hits your detector. If you image a star, which is effectively a point source because it's so far away, the star doesn't appear as a single pixel. It spreads out into a small blob due to diffraction, atmospheric turbulence, and the optics of your telescope. A good telescope with good seeing conditions produces a tight, symmetric PSF. A mediocre setup or bad atmospheric conditions produces a bloated, irregular PSF. When you stack multiple frames, you're averaging out the random variations in the PSF, sharpening the image. Stacking is a standard technique in astrophotography. It works because noise is random, but signal is consistent. Average enough frames together, and the signal emerges while the noise cancels out. But stacking can also introduce artifacts if your alignment is off, or if the object is moving relative to the background stars. Motion blur is one of the first things skeptics brought up. 3i Atlas is moving. Earth is moving. The telescope is tracking the stars, not the comet. If the exposure is long enough, the comet should smear into a line, right? That's what happens with asteroids when you do long exposures. They trail across the frame because they're moving relative to the background. But here's the thing. Motion blur has a signature. It's directional. It follows the object's trajectory. It's uniform along the length of the trail, and critically it affects the PSF in a predictable way. A smeared object has a blurred leading edge and a blurred trailing edge, with the brightness tapering off at both ends. Tiago's images don't show that. The elongation isn't a smear, it's structured. It has edges. It doesn't taper the way a motion-blurred trail would. And when you calculate the expected motion blur based on the object's known speed and the exposure time, it doesn't match. The elongation is too pronounced, oriented at the wrong angle, persistent across frames with different exposure lengths. Camera artifacts are the next suspect. Maybe the sensor has a defect. Maybe there's a cosmic ray hit that looks like structure. Maybe the image has been over-sharpened in processing, creating ringing or edge artifacts that mimic a shape. Tiago addressed this by showing that the object moves across the frame in different images. If it were a sensor defect, it would stay in the same pixel coordinates no matter where the telescope pointed. It doesn't. The object moves with the sky, which means it's external to the camera. Cosmic rays do hit sensors, especially in space, but they create bright streaks or single pixel spikes, not extended shapes that persist across dozens of frames. Sharpening artifacts can enhance edges, but they don't create structure out of nothing. If you over-sharpen a round, diffuse blob, you get a round diffuse blob with emphasized edges. You don't get a cigar. And again, the shape is visible in the unstacked, unprocessed frames. It's there in the raw data, before any human intervention. Atmospheric turbulence is the third usual suspect. Earth's atmosphere is a mess of turbulent cells, each refracting light slightly differently. This causes stars to twinkle and blurs fine detail in telescopic images. Could atmospheric seeing stretch 3i Atlas into an elongated shape? Atmospheric distortion is random and time-varying. Over the course of seconds or minutes, the distortion changes. If you stack frames taken over an hour, the atmospheric effects average out, leaving you with a sharper image. They don't consistently create the same elongation in the same direction across all frames. That's not how turbulence works. Turbulence smears, blurs and jiggles. It doesn't sculpt. And critically, ESA's images were taken from space, with no atmosphere between the camera and the object. Mars's atmosphere is thin and wispy, and the cameras are above it. No atmospheric turbulence. Same, elongated shape. That's a kill shot for the turbulence hypothesis. One skeptic downloaded Tiago's raw frames, imported them into professional image analysis software, and spent an entire weekend trying to make the object look normal. They adjusted alignment parameters, tried different stacking algorithms, applied various filters. They were looking for the combination of settings that would turn the cigar into a round, normal-looking comet. They couldn't find it. Every method they tried preserved the elongation. They even tried manually aligning the frames in ways that should introduce artifacts, just to see if they could force the result. The elongation persisted. Finally, they posted their findings online with a reluctant conclusion. Whatever this is, it's in the data. It's not an artifact. That post got thousands of views and hundreds of comments. It shifted the conversation. People stopped asking whether the image was real and started asking what it meant. An imaging specialist, someone who works on planetary missions and knows the ins and outs of space-based cameras, weighed in. They noted that Cassis has been imaging Mars for years. Its PSF is well characterized. Its optical aberrations are known and corrected in processing. When Cassis images 3i Atlas and shows the same elongated morphology as Tiago's ground-based capture, you can rule out the entire class of instrumental artifacts, two completely independent systems with different optics, different sensors, different processing pipelines, producing the same result. That's not coincidence. That's consistency. And consistency in science is how you separate real phenomena from observational flukes. The specialist concluded, whatever this object is, its appearance is intrinsic, not imposed by the act of observation. It looks like this because that's what it looks like. So if not artifact, then what? If the images are showing us something real, something physical, then we need to start talking about the object itself. We need to move from forensics to physics. We need to ask, what natural processes could make a comet look like this? And if no natural processes fit, what unnatural processes might? That's where things get really interesting, because once you lock in the data, once you confirm the images aren't lying, you're forced to confront the implications, and the implications spread outward like cracks in ice, threatening to shatter everything we thought we understood about what's out there, moving through the dark, passing through our neighbourhood on trajectories we never authorised. The question isn't whether the images are real anymore. The question is, what are we looking at, and why does it look so wrong? Hold that thought, because before we jump to exotic explanations, we need to exhaust the normal ones. We need to talk about cometary physics, about all the weird, wonderful and deeply strange things that ice and rock can do when they're hurtling through space, baking in. Sunlight bleeding gas into the void. Part 7. Cometary mechanisms that could mislead. Comets are not simple objects. They're dirty snowballs, sure, but that phrase hides astonishing complexity. A comet nucleus is a jumble of water ice, carbon dioxide ice, methane ice, ammonia ice, all mixed with rock dust, organic compounds, and God knows what else. When a comet approaches the Sun, different ices sublimate at different temperatures. Water ice starts outgassing beyond the orbit of Mars. Carbon dioxide ice starts earlier. The gas jets don't spray evenly. They erupt from specific vents on the surface, creating asymmetric pressure that can spin the nucleus, change its orbit, and sculpt the coma into bizarre shapes. Comets fragment. They flare. They develop anti-tails that point toward the sun instead of away. They're unpredictable, messy, and full of surprises. So when we see something weird, the first instinct is to ask, could this just be normal comet weirdness taken to an extreme? Dust-poor comets are a real thing. Most comets are dirty snowballs, but some are more snowy than dirty. They have less dust mixed into the ice, so when they outgas, the coma is mostly transparent gas rather than opaque dust. Gas is harder to see than dust. It doesn't scatter sunlight as efficiently. You need spectroscopy to detect it, looking for emission lines from molecules like hydroxyl, cyanide, or carbon monoxide. From a distance, a dust-poor comet can look much fainter than you'd expect, and its tail can be almost invisible. Could 3i Atlas be a dust-poor comet, producing a gas coma that's too faint for Tiago's telescope and ESA's cameras to resolve? Maybe, but that doesn't explain the elongated shape. A gas coma should still be roughly spherical, or at least diffuse. It shouldn't have the dense, structured appearance we see in the images, and if it's outgassing enough to produce a bright coma visible from Earth and Mars, it should be producing some kind of tail, even a faint one. The absence is the problem. The anti-tail effect is another cometary trick that can confuse observers. Normally, a comet's tail points away from the sun because solar radiation pressure and the solar wind blow dust and gas outward. But if you observe a comet from just the right angle, you can see dust particles along the comet's orbital plane backlit by the sun, creating a tail that appears to point toward the sun. It's an optical illusion caused by geometry. Anti-tails are rare but documented. Could this explain the lack of a visible tail in 3i Atlas? The problem is timing and geometry. Multiple observations over weeks should show different viewing angles. If the anti-tail effect were hiding the real tail, we'd expect to see the tail emerge as our perspective changed. It doesn't. And again, this doesn't explain the elongated nucleus. An anti-tail is about where the tail appears to point, not about the shape of the central object. Anisotropic outgassing is when jets of gas erupt from specific spots on the nucleus, rather than uniformly across the surface. If you have a strong jet pointing in one direction, it can create an elongated coma in that direction, making the comet look lopsided or stretched. This is well documented in comets like Halley, where the Giotto spacecraft flew past in 1986 and imaged powerful jets erupting from the nucleus. Could 3i Atlas have jets that create the appearance of elongation? Possibly, but there are problems. Anisotropic outgassing usually creates a fan-shaped or cone-shaped structure, not a cigar. The jets are brightest near the nucleus and fade as the gas disperses. Tiago's images and ESA's images show a dense, relatively uniform elongation, not a jet plume, and jets should vary as the nucleus rotates. If the elongation were caused by a jet, we'd expect it to change orientation or brightness over time as different parts of the nucleus face us. Multiple observations don't show significant variation. The shape is persistent. Fragmentation is another possibility. Comets can break apart due to tidal stress, thermal stress, or rotational stress. When they do, you get multiple fragments travelling together, sometimes in a line. This can create an elongated appearance in low-resolution images. Could 3i Atlas be a fragmenting comet? If it were, we'd expect to see the fragments separate over time. Observations weeks apart should show the pieces drifting farther from each other. That doesn't seem to be happening. The morphology is stable, and fragmentation usually triggers intense outgassing as fresh ice is exposed, creating bright comas around each fragment. We're not seeing that. We're seeing one dense object, not multiple pieces trailing each other. Fragmentation doesn't fit. Each of these explanations has a kernel of truth. Comets can be dust poor. They can produce anti-tails. They can have anisotropic jets. They can fragment. But when you try to apply any of these mechanisms to 3i Atlas, they fail to explain the full set of observations. The elongated shape is too persistent. The lack of a tail is too complete. The consistency between Earth-based and Mars-based views is too exact. You can twist yourself into knots trying to make the normal explanations work, invoking unlikely combinations of geometry, composition, and timing. But at some point, Occam's razor cuts the other way. At some point, the simplest explanation is that this isn't a normal comet, it's something else. Mainstream media outlets like The Guardian have covered 3i Atlas, noting the anomalies but carefully steering away from the alien angle. They frame it as a curious scientific puzzle, which is fair. Most curious scientific puzzles turn out to have boring answers, but boring answers still need to fit the data, and so far, none of the boring answers do, so we're left with a choice. Either we keep searching for the natural explanation that fits, accepting that we might be dealing with comet physics we don't fully understand yet, or we start considering explanations that don't fit the comet category at all, explanations that might be natural but exotic, or explanations that might not be natural at all. That's the fork in the road where 3i Atlas has left us. And standing at that fork, looking down both paths, it's hard not to feel a creeping sense of unease, because one path leads to new science, and the other leads to something we're not ready for. So let's walk down the second path just for a moment. Let's talk about the exotic possibilities, the ones that make your skin crawl. Part 8. Exotic but scientific alternatives. Science thrives on the edge cases, the outliers, the phenomena that don't fit neatly into existing models. Every major discovery in history started as an anomaly someone couldn't explain. Pulsars were initially called LGM signals, for little green men, because the regular radio pulses seemed too precise to be natural. Turns out they were rotating neutron stars, natural but utterly alien to our everyday experience. Gamma-ray bursts were a mystery for decades until we realized they were the death screams of stars collapsing into black holes, releasing more energy in seconds than the sun will emit in its entire lifetime. The universe is weirder than we imagined, and it's probably weirder than we can imagine. So when something doesn't fit, when the normal explanations fail, we need to consider the exotic ones. Not aliens first, but the extreme edges of natural physics. The stuff that's real but rare, documented but poorly understood. Hypothesis 1. 3i Atlas is a porous icy aggregate, a loosely bound collection of ice grains held together by their own weak gravity. Think of it like a cosmic dust bunny, more void than solid. When an object like this approaches the sun, the sublimation doesn't happen uniformly. Ice deep inside the structure can turn to gas, creating pressure that vents through cracks and pores. The outgassing might be subsurface, invisible to external observers, which could explain the lack of a visible tail. The porous structure might also allow the object to hold a non-spherical shape without collapsing, explaining the elongation. This isn't pure speculation. We know some comet nuclei have very low densities, suggesting porosity. The problem is that porous objects should still produce visible outgassing if they're bright enough to image. And the elongation would need to be extreme and stable, which requires the object to be either non-rotating or rotating around its long axis. Both scenarios are unlikely, but not impossible. Hypothesis 2. Directional jets creating a fin-like coma. Imagine a comet nucleus with jets that fire in two opposite directions along its rotation axis, creating a dumbbell-shaped coma. From certain viewing angles, this could appear elongated like a cigar or a fin. The jets would need to be strong and highly collimated, funneled through narrow vents, and the nucleus would need to be rotating in just the right way. This is exotic, but not impossible. The European Space Agency's Rosetta mission to comet 67P/Churyumov-Gerasimenko showed jets behaving in complex ways. But Rosetta also showed those jets creating visible dust tails. 3i Atlas doesn't have one. And again, the morphology would need to be stable across multiple viewing angles, which is a tall order for a dynamic jet system. Hypothesis 3. An interstellar shard. Not a comet, not an asteroid, but something in between. Imagine a fragment of a larger body that was shattered in some ancient collision, ejected into interstellar space, and has been wandering the galaxy for millions of years. Its composition might be exotic, rich in carbon monoxide ice or other volatiles that sublimate at unusual rates. Its shape might be inherently elongated because it's a shard, a splinter, a piece of something bigger. When it enters our solar system and gets close to the sun, it outgasses just enough to create a faint coma, but not enough to develop a long tail. This hypothesis has the advantage of explaining both the weird shape and the weird orbit. Interstellar objects don't have to follow the rules that govern solar system natives. They can have high inclinations, unusual compositions, bizarre morphologies. Oumuamua might have been one of these. 3i Atlas might be another. The sample size is still too small to know what's normal for interstellar visitors. Hypothesis 4. An engineered object. This is where we step off the cliff into the territory Avi Loeb has been exploring. Imagine a light sail, a thin reflective structure designed to catch starlight and use it for propulsion. Light sails are real technology, we've built them. Japan's Ikaros spacecraft demonstrated solar sailing in 2010. The Planetary Society's Light Sail 2 launched in 2019 and successfully raised its orbit using sunlight. These are small-scale demonstrations, but the physics scales up. A sufficiently large, sufficiently thin light sail could travel between stars, accelerating slowly over centuries or millennia. If 3i Atlas were a light sail, its elongated shape would make sense. Sails are thin and flat. From edge on, they'd look like a line. From an angle, like a cigar. The lack of a tail would make sense. There's no outgassing because there's no ice. The brightness would come from reflected sunlight off the sail's surface. The trajectory anomalies would make sense. A sail can maneuver, adjusting its orientation to change its path. Each of these hypotheses makes predictions. The porous aggregate should show specific spectral signatures, absorption bands from water ice and organics. The directional jets should vary as the nucleus rotates, changing brightness and orientation over hours or days. The interstellar shard should show spectral, lines from exotic ices, maybe carbon monoxide or methane dominating over water. The light sail should have an extremely high albedo, reflecting a huge fraction of the light that hits it, and should show no spectral features from ices or minerals, just reflected sunlight. Spectroscopy is how you test these ideas. Point a spectrograph at 3i Atlas, spread its light into a spectrum, and look for the fingerprints of specific molecules. That data exists, or could be collected, but it hasn't been released publicly yet, and that's frustrating, because we're stuck in this limbo where the images show something weird, the hypotheses make predictions, but we don't have the data to confirm or refute them. If 3i Atlas is engineered, the implications are staggering. It would mean we're not alone. It would mean someone else built technology, launched it into space, and we've stumbled across it. Are they watching us? Did they send it here on purpose? Is it a reconnaissance probe gathering data to send back to wherever it came from? Or is it ancient debris, a relic from a civilization that died out millions of years ago, now drifting through the galaxy like a ghost ship? These questions spiral outward into philosophy, into history, into the entire framework of human meaning. But before we go there, we need to acknowledge something. The alien hypothesis is the last resort, not the first. You exhaust every natural explanation before you invoke intelligence. That's the scientific method. That's how you avoid fooling yourself. But when the natural explanations keep failing, when the data keep pointing in an uncomfortable direction, you can't ignore it forever. And the data aren't the only thing driving this story. The human reaction matters too, because science doesn't happen in a vacuum. It happens in a social context shaped by who has access to information, who decides what gets shared, and who gets listened to. Part 9. Social Dynamics and Information Ecology. Tiago's images hit X, formerly known as Twitter, on September 28, 2024. Within hours, the post had hundreds of engagements. Within days, thousands. By the time ESA released their images 2 weeks later, Tiago's capture had become a viral phenomenon, discussed in forums, analysed in blog posts, debated in comment sections across the internet. This isn't how astronomy news usually spreads. Normally a discovery gets submitted to a journal, undergoes peer review for months, gets published behind a paywall, and then maybe gets picked up by science journalists who write accessible summaries for the public. By the time you hear about it, the discovery is old news to the people who made it. But social media has changed the game. An amateur astronomer with a decent telescope and an internet connection can break news faster than any institution. And if their data are good, if they're transparent about their methods, they can build credibility in real time. The timeline is revealing. Tiago posts on September 28th. The post gains traction organically, shared by other amateur astronomers, by space enthusiasts, by people fascinated by the anomaly. Influencers with large followings pick it up and amplify it. By early October, mainstream media outlets are covering it. Motor Biscuit, a site about cars, runs a story because their audience loves anything space-related and weird. Tech blogs follow. Then ESA drops their images on October 11th, and the story explodes again. The amateur astronomer was right. The professional confirmation validates him. Suddenly Tiago isn't just some guy with a telescope. He's the person who spotted something before the institutions did. That credibility is powerful. It shifts the conversation from whether the images are real to what they mean. Amateur credibility in astronomy has a long history. Caroline Herschel discovered 8 comets in the late 1700s, working with her brother William. Eugene Shoemaker and his wife Caroline discovered dozens of comets and asteroids, including Shoemaker-Levy 9, which famously crashed into Jupiter in 1994. Amateur astronomers monitor variable stars, track supernovae, discover near-Earth asteroids. The tools have gotten better and cheaper, democratizing access to the sky. Today, a determined amateur with a few $1,000s in equipment can do science that would have required a professional observatory a generation ago. Tiago's part of that tradition. He's not an outsider shouting in the wilderness. He's a participant in a global network of observers contributing real data. But transparency is what separates credible amateurs from cranks. Tiago shared his raw frames. He explained his equipment and methods. He invited scrutiny. When skeptics downloaded his data and tried to debunk it, they couldn't, and they admitted as much publicly. That's the gold standard. Contrast that with the usual UFO sighting: blurry phone video, no metadata, wild claims, refusal to engage with criticism. Those stories collapse under examination. Tiago's didn't. The data held up. And because the data held up, the conversation shifted. People started asking not whether it was real, but what it was. That shift is everything. NASA and ESA are caught in a different dynamic. They have to be cautious. They represent governments, international partnerships, billions of dollars in funding. A premature claim that turns out to be wrong can destroy credibility, tank funding, and become a political football. So they err on the side of caution, releasing information slowly, hedging their statements, avoiding speculation. That caution is rational from their perspective, but it creates a vacuum. The public wants answers now. Social media wants drama now. And when institutions stay silent or speak in careful jargon, that vacuum fills with speculation, conspiracy theories, and frustration. The tension between institutional caution and social urgency is real, and it's growing. There are historical precedents for amateurs forcing professional revisions. Tabby's star, officially known as KIC 8462852, was flagged by citizen scientists analysing data from NASA's Kepler Space Telescope. The star showed bizarre dimming patterns that didn't match any known natural phenomenon. Speculation ranged from dust clouds to comets to, yes, alien megastructures. Professional astronomers were initially skeptical, but the data were undeniable. It took years of follow-up observations to narrow down the explanations, and the mystery still isn't fully solved. But the point is, the amateurs were right to flag it. They saw something real that deserved investigation. Shoemaker-Levy 9 is another example. Amateur astronomers tracked the comet's fragments as they lined up to slam into Jupiter. Their observations coordinated the professional response, ensuring telescopes around the world were pointed at the right place at the right time. Amateurs matter, they always have. X, formerly Twitter, has become a kind of instant peer review platform. Post something, and within hours, experts and enthusiasts will dissect it. Good data survives scrutiny. Bad data gets shredded. It's messy, it's chaotic, but it works surprisingly well for filtering signal from noise. Tiago's images survived that gauntlet. People tried to find the flaw, the mistake, the hoax. They couldn't. And that failure to debunk became its own kind of validation. Credibility layering is the phenomenon where one trusted voice can tip the scales. If Tiago had been a random anonymous account with no history, his images might have been dismissed. But he had a track record. He'd been sharing astrophotography for years. People knew him. When he said this looks weird, people listened. And when ESA confirmed it, the layers of credibility stacked up into something solid. Of course, the conspiracy chatter is out there too. Cover-up, soft disclosure. The idea that governments know more than they're saying and are slowly preparing the public for a big reveal. I'm skeptical of that narrative. Not because governments are always transparent, they're not. But because the number of people who'd need to keep a secret that big is implausibly large. Scientists talk. Data leak. Whistleblowers emerge. The simpler explanation is that institutions are slow, cautious, and bad at communication. Not that they're hiding alien contact. But the fact that people are talking about cover-ups tells you something about trust. When institutions don't share data quickly, when they speak in hedge language, people fill the gaps with suspicion. That's the information ecology we're living in, and that ecology shapes what gets investigated and what gets ignored, which brings us to the politics of data access. Part 10. Controversies, Data Access, Transparency, and Politics. Science is supposed to be open. Data collected with public funding should be publicly accessible. Results should be reproducible. That's the ideal. The reality is messier. Data processing takes time. Raw data from space missions are often huge, requiring calibration, cleaning, and formatting before they're useful. Releasing data prematurely can lead to misinterpretations, false positives, and public confusion. So agencies build data pipelines with checkpoints, reviews, and scheduled releases. The process is designed to ensure quality. But from the outside, it looks like gatekeeping. And when something interesting is happening, when people are hungry for information, those delays fuel frustration and suspicion. ESA's data processing pipeline for CAS's images involves multiple stages. Raw frames come down from the trace gas orbiter. They're calibrated using dark frames and flat fields to remove sensor artifacts. Geometric distortions are corrected. The images are radiometrically calibrated so brightness values correspond to physical units. Then they're archived and released to the Planetary Science Archive, ESA's public repository. This process can take weeks or months depending on the mission's priorities and staffing. For routine observations, the delay is acceptable. For something potentially extraordinary like 3i Atlas, the delay is maddening. People want the raws, they want the timestamps, the metadata, the full spectroscopic data, they want to do their own analyses, and they want it now. Public frustration is palpable in the online discussions. Where are the raw frames? Why hasn't ESA released spectroscopy data? What are they hiding? The language of suspicion creeps in. Now there might not be anything nefarious. The data might not exist yet because spectroscopic observations haven't been scheduled, or the data might be in the pipeline waiting for calibration, or the mission team might be writing a paper and wants to publish before releasing the data to maintain priority. These are normal parts of the scientific process, but to the public, especially a public primed by decades of UFO secrecy narratives, it looks like stonewalling, and stonewalling creates conspiracy space. NASA and ESA use cautious language because they have to. Saying this might be aliens without overwhelming evidence would be career-ending for the scientists involved and damaging to the agencies. So they say, we observed interesting features. We're continuing to analyze the data. We encourage further observations. That's responsible science communication. But it's also deeply unsatisfying when you're staring at images that look like nothing you've ever seen. The social urgency, driven by viral posts and media coverage, demands immediate answers. The scientific process, driven by the need to avoid false positives and maintain credibility, demands patience. The collision of these two timescales creates tension. Why do scientists delay? Because false positives are expensive. If you claim a discovery and you're wrong, you lose credibility, you lose funding, and you become a cautionary tale. The cold fusion debacle in 1989, where scientists announced they'd achieved fusion at room temperature and then couldn't replicate it, haunts the field to this day. Faster-than-light neutrinos, announced in 2011 and retracted in 2012 after a loose cable was found to be the culprit. Every false positive makes it harder for real discoveries to be taken seriously. So scientists are conservative. They triple-check everything. They look for every possible source of error, and only when they're confident do they go public. That conservatism protects science, but it also creates a trust gap with a public that doesn't understand why answers take so long. But secrecy, even justified secrecy, creates conspiracy space. People fill the gaps with their own narratives. If the data exist and aren't being released, maybe it's because they show something uncomfortable. Maybe the spectroscopy revealed an artificial signature, and the agencies are trying to figure out what to do before going public. Maybe there's a protocol for this, buried in some classified annex to a treaty, and the slow rollout is deliberate soft disclosure. I don't believe these narratives, but I understand why they emerge. When information flow is restricted, speculation fills the void. Specific requests from the community are reasonable. Release the raw frames from CASs, provide timestamps and metadata, share any spectroscopic observations that have been made. Open the data to independent analysis. Let 1,000 researchers dig into it and see what they find. That's the open science ethos, and it's how major discoveries get validated. The Human Genome Project succeeded in part because of its commitment to immediate public data release. Anyone could download the sequences and analyze them. That transparency built trust and accelerated progress. Astronomy should follow that model, especially for objects of high public interest. 3i Atlas qualifies. The comparison to UFO and UAP secrecy debates is unavoidable. The US government spent decades denying that it tracked unidentified aerial phenomena. Then in 2017, the New York Times published leaked videos from Navy pilots encountering objects with flight characteristics that defied explanation. The Pentagon eventually confirmed the videos were real. A task force was formed. Congressional hearings were held. But the process was slow, grudging, full of redactions and classified annexes. The pattern eroded trust. People started assuming that any delay or obfuscation meant something was being hidden, and maybe sometimes it was. Maybe sometimes it wasn't, but the bureaucracy just moves slow. Either way, the effect is the same, a collapse of trust. Astronomy doesn't want to go down that road. Open data, rapid sharing, transparent communication. That's how you build trust. That's how you avoid the conspiracy spiral. So where does that leave us? Stuck in a cliffhanger. We have images that show something weird. We have hypotheses that range from exotic natural physics to alien technology. We have institutional caution colliding with social urgency. We have enough data to know something's off, but not enough to know what. And we're waiting. Waiting for more observations. Waiting for spectroscopy. Waiting for someone, somewhere, to release the information that tips the balance. The truth might be stranger than a comet, but if no one's willing to admit it yet, we're left hanging in the uncertainty. And uncertainty, when it comes to questions this big, is almost unbearable. But 3i Atlas isn't the only recent discovery shaking up our understanding of the cosmos. Let's zoom out and look at what else has been happening in astronomy this year. Part 11. Enceladus Organics Revival. Cassini died in 2017. The spacecraft, which had spent 13 years exploring Saturn and its moons, was deliberately plunged into the planet's atmosphere to avoid contaminating potentially habitable moons like Enceladus. It was a Viking funeral for one of humanity's greatest explorers, but the data Cassini collected didn't die. Gigabytes of measurements, images, spectra, sitting in archives, waiting for someone to take another look with new tools, new models, new questions, and that's exactly what happened in 2024. A team of scientists reanalyzed data from Cassini's flybys of Enceladus, the tiny ice-covered moon that shoots geysers of water into space from cracks in its surface. They found complex organic molecules, the building blocks of life, more diverse and abundant than anyone realized. It's like finding an old VHS tape in your attic and realizing it's evidence of something extraordinary. Enceladus has been a target of astrobiological interest since Cassini first detected its plumes in 2005. The moon has a subsurface ocean, kept liquid by tidal heating from Saturn's gravity. The plumes erupt through cracks called tiger stripes near the South Pole, spraying water vapor, ice particles and trace gases into space. Cassini flew through the plumes multiple times, analyzing their composition with mass spectrometers. Early results showed water, salts, and simple organics like methane and carbon dioxide. Interesting, but not shocking. Lots of places in the solar system have simple organics. But the new analysis, using improved calibration techniques and better models of how the instruments respond to complex molecules, found something more. Amino acids, or at least precursors to amino acids. Large carbon-based molecules with nitrogen and oxygen. The kind of chemistry you associate with life. This discovery highlights the importance of reanalysis. Scientific instruments are never perfect. Data processing involves assumptions, models, choices about what to emphasize and what to filter out. As our understanding improves, we can go back to old data and extract new insights. The Viking landers on Mars, which touched down in 1976, conducted experiments looking for signs of life. At the time, the results were ambiguous and mostly interpreted as negative. Decades later, scientists reanalyzed the data with better understanding of Martian soil chemistry. Some now argue the original experiments might have detected microbial life after all, but the interpretation was too conservative. Whether that's true is still debated, but the point stands. Old data can hide new discoveries. 3i Atlas is generating data right now. Those data will live in archives for decades. Someone in 2050 might look at our images, apply techniques we haven't invented yet, and see something we missed. The organics on Enceladus matter because they push the moon closer to the threshold of habitability. Liquid water, check. Energy source from tidal heating, check. Organic molecules, check. That's 3 out of 3 ingredients for life as we know it. It doesn't mean Enceladus has life. It means it could, and that possibility motivates future missions. NASA and ESA are planning concepts for orbiters and landers that could sample the plumes directly, looking for biosignatures, for patterns in the chemistry that scream life rather than just chemistry. If we found life in Enceladus's ocean, it would be the second Genesis, proof that life can arise independently in multiple places. The implications would reverberate through every field of science and philosophy. The connection to 3i Atlas is indirect but real. Both stories are about pushing the boundaries of what we think is possible. Both are about looking at ambiguous data and asking, what if? Enceladus reminds us that the solar system hides surprises. Europa, another ice-covered moon with a subsurface ocean, might harbour life. Titan, Saturn's largest moon, has liquid methane lakes and a thick organic haze. Mars might have subsurface brine pockets where extremophils cling to existence. We're learning that habitable doesn't mean Earth-like. It means liquid solvent, energy, and chemistry. Those conditions are more common than we thought, and if life can arise in so many places, maybe intelligence can too. Maybe technology can too. Maybe the galaxy is lousy with civilizations, some of them sending probes out to explore, just like we do. Speculative thought. Could interstellar objects like 3i Atlas be carriers of organics? Panspermia, the idea that life spreads between planets or even star systems via asteroids and comets, is an old hypothesis. Microbes could survive in the frozen interior of a rock, ejected from one world and caught by another. Complex organics could be synthesized in interstellar space, on grain surfaces in molecular clouds, and incorporated into comets. When those comets visit solar systems, they deliver raw materials for life. 3i Atlas, whatever it is, has travelled through interstellar space for who knows how long. If it's a comet, it might carry organics from its home system, chemistry shaped by alien stars, alien planets, alien processes. Studying it could teach us about the chemical diversity of the galaxy. Or if it's not a comet, studying it could teach us something else entirely. Transparency matters here too. The Cassini reanalysis was possible because the data were public. Anyone could download them, run their own analysis, publish their findings. That openness accelerates discovery. If Enceladus's data had been locked away, we might still not know about the complex organics. The same principle applies to 3i Atlas. The more data we release, the more minds we engage, the faster we converge on the truth. Secrecy slows progress. Openness speeds it up. And when the stakes are this high, when the questions touch on the existence of life beyond Earth, we can't afford to be slow. So if Saturn's moon might hide life potential, what does that say about interstellar visitors? What might they carry or be? Part 12. Near-Earth Object Skimming Satellites. In early October 2024, a small asteroid made headlines by passing between Earth and the ring of satellites orbiting our planet. The object, designated 2024 TQ8, zipped past at a distance of about 100,000 kilometers, well inside the orbit of geostationary satellites at 36,000 kilometers. It wasn't a threat. Objects this size, maybe 10 meters across, burn up in the atmosphere if they hit. But the close pass triggered alerts, mobilized observers, and reminded everyone how crowded and chaotic near-Earth space is becoming. The asteroid was traveling at roughly 50,000 kilometers per hour relative to Earth. Blink, and it's gone. The detection and alert happened fast, coordinated by automated sky surveys and the International Near-Earth Object Network. The trajectory was spectacular. Visualizations show the asteroid threading the needle between Earth and our satellite constellations, a cosmic near-miss in the grand scheme but routine for astronomers who track these things. Thousands of near-Earth asteroids are catalogued. Hundreds are discovered every year. Most pass harmlessly. A few hit, like the Chelyabinsk meteor in 2013, which exploded over Russia and shattered windows across a wide area. The NEO community is good at this. They have automated telescopes scanning the sky every night. They have software that calculates orbits, predicts close approaches, and flags potential threats. When an object is discovered, the data are shared within hours. observatories around the world follow up, refining the orbit, determining the object's size and composition. This rapid sharing is what transparency looks like. No one hoards NEO data because the threat is universal. An asteroid doesn't respect borders. If it's going to hit, everyone needs to know, so the culture in the NEO community is open by necessity. Data go into public databases. Orbits are calculated and published. Anyone can access them. That openness has made the field incredibly effective. We've gone from knowing a handful of near-Earth asteroids in the 1990s to tracking over 30,000 today. And when something new appears, the community mobilizes. Amateurs contribute observations. Professionals refine calculations. Everyone works together because the stakes are clear. So here's the contrast that gnaws at me. Why can we mobilize so effectively for a 10-meter rock that poses minimal threat, but we're sluggish and secretive when it comes to 3I Atlas, an interstellar visitor exhibiting genuine anomalies? The near-Earth object skimmed past. Data was shared immediately. Trajectory was calculated, story was told, and we moved on. All within days. 3I Atlas has been under observation for weeks. Images show consistent weirdness. Multiple instruments confirm the anomaly, and we're still waiting for comprehensive data release. What's the difference? Is it institutional inertia? Is it caution about making claims that might prove embarrassing? Or is there something else, something more deliberate, about how we handle objects that don't fit our expectations? The speed of NEO response demonstrates what's possible when the community agrees on priorities. Automated surveys like the Catalina Sky Survey, Pan-STARRS, and the upcoming Vera Rubin Observatory scan huge swaths of sky every night. When they spot something moving, algorithms flag it, calculate preliminary orbits, and distribute alerts. Within hours, observers worldwide can point their telescopes at the coordinates and gather more data. That distributed network is powerful, it's resilient, no single point of failure. If one observatory is clouded out, others pick up the slack. The system works because everyone shares data immediately and freely. There's no competitive advantage to hoarding information about an asteroid that might hit Earth. But 3I Atlas isn't a threat in the collision sense. It's not going to hit us. Its orbit is well determined. So maybe that's why the urgency is different. There's no immediate danger, no need for rapid response, no planetary defense implications. It's scientifically interesting, sure, but interesting doesn't trigger the same mobilization protocols as dangerous. Except that logic only holds if you assume 3I Atlas is just an unusual comet. If it's something else, if the anomalies are pointing towards something genuinely extraordinary, then the scientific value alone should justify rapid data sharing. Understanding what this object is could reshape our understanding of interstellar space, cometary physics, or even the prevalence of technology in the galaxy. That's worth urgency. The question becomes, could institutional inertia be deliberate? Not in the sense of conspiracy, but in the sense of bureaucratic self-preservation. If you release data that turn out to support a wild interpretation, and that interpretation spreads through media and becomes a public spectacle, and then it turns out to be wrong, the institution looks bad. Funding gets questioned. Credibility erodes. Politicians make speeches about wasted money. So the incentive structure pushes toward caution, toward waiting until you're absolutely certain before saying anything definitive. That's rational from the institution's perspective. But it's frustrating for everyone else, and it creates space for speculation to flourish unchecked. If aliens were probing our solar system, would space agencies tell us? That's the thought experiment that keeps popping up in discussions about 3I Atlas. The official position is, of course, they would. NASA has protocols for announcing the detection of extraterrestrial intelligence. The SETI community has drawn up guidelines for confirming and communicating such a discovery. Transparency is supposedly baked into the process, but protocols on paper don't always match reality under pressure. If you detected something genuinely extraordinary, something that would cause social upheaval, economic disruption, or existential panic, would you really just hold a press conference and announce it? Or would there be quiet conversations first, risk assessments, consultations with governments, careful planning about how to frame the message? I don't know. I hope the answer is transparent and immediate announcement. But I can imagine scenarios where caution becomes delay, and delay becomes secrecy. The near-Earth object story is clean, satisfying, resolved. Rock approaches, we track it, it passes, we learn its properties, we move on. 3i Atlas is messy, unresolved, lingering. Object approaches. We image it. It looks wrong. We argue about what it means. We wait for more data. One story has closure. The other doesn't. And humans crave closure. We want the answer. That's why the comparison between these two stories matters. It shows what astronomy looks like when it's working well versus what it looks like when we're stuck in uncertainty. And uncertainty, especially about something potentially this significant, is corrosive. It eats away at trust. It breeds speculation. It makes people wonder what's being hidden, even when nothing is. But let's zoom out even further. Because 3i Atlas and near-Earth asteroids aren't the only space stories from 2024 that challenge our assumptions. Part 13, Rare Gravitational Lensing, Dark Matter Clump. In September 2024, astronomers announced the detection of an unusual gravitational lensing event that might reveal a dark matter clump or an exotic gravitational anomaly. Gravitational lensing is one of the most elegant confirmations of Einstein's general relativity. Massive objects bend space-time. Light travelling through that bent. Space-time follows curved paths. When a massive galaxy or cluster sits between us and a more distant object, it acts like a lens, magnifying and distorting the background light. We see arcs, rings, multiple images of the same distant galaxy. It's beautiful and it's useful. By measuring the lensing, we can map the mass of the foreground object, including the dark matter we can't see directly. This particular detection involved microlensing, a subtler version where a smaller mass, maybe a rogue planet or a dark matter clump, passes in front of a distant star and briefly brightens it. The light curve, the graph of brightness over time, has a distinctive shape that reveals the mass and motion of the lensing object. The September event showed a light curve that didn't quite match expectations. The magnification was too strong, or the duration was wrong, or multiple lensing events overlapped in a way that suggested structure we can't see. The details are still being worked out, but the implication is clear. There's invisible mass out there, clumped in ways we don't fully understand. It's like finding a fingerprint in fog. You can't see the hand that left it, but you know it was there. Dark matter makes up 85% of the matter in the universe. We know it exists because galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters bend light more than their visible mass should allow. The cosmic microwave background, the afterglow of the Big Bang, has patterns that require dark matter to explain. But we don't know what it's made of. Particles we haven't discovered? Primordial black holes? Something even stranger? Detecting a dark matter clump-through lensing is a step toward answering that question. It tells us dark matter isn't smoothly distributed. It has structure. It clumps. And if it clumps, maybe we can study those clumps, figure out their properties, narrow down the list of candidates. Why does this matter for 3i Atlas? Because it proves the cosmos hides invisible structures, things that don't emit light, don't interact with normal matter except through gravity, but shape the universe in profound ways. If dark matter clumps can hide in plain sight, detectable only through their gravitational effects, what else might be hiding? Could alien probes use materials or technologies that don't emit light in ways we'd recognize? Could they be out there, invisible to our telescopes unless we know exactly where to look and what to look for? I'm not saying 3i Atlas is dark matter or cloaked alien tech. I'm saying the universe is full of surprises, and our ability to detect things is limited by the tools we use and the assumptions we make. Historical precedent matters. The Einstein cross, a gravitationally lensed quasar creating 4 images of the same distant object, was predicted by theory before it was observed. When it was finally found in 1985, it confirmed Einstein's equations in spectacular fashion. The Eddington Eclipse expedition in 1919 measured the bending of starlight by the sun during a solar eclipse, providing the first experimental confirmation of general relativity. These observations were paradigm-shifting. They took ideas that sounded absurd, like space-time bending, and showed they were real. Gravitational lensing has since become a workhorse tool in astronomy, used to study everything from exoplanets to the large-scale structure of the universe. But it started as a wild prediction that required extraordinary evidence to confirm. 3i Atlas needs that kind of rigor. If the anomalies are real, if the object truly doesn't fit the comet model, we need multi-method confirmation. Spectroscopy to analyze composition, radar to measure shape and rotation, long-term photometry to track brightness variations, multi-wavelength observations from radio to X-ray, parallax measurements from different vantage points to nail down the three-dimensional structure. Every tool we have should be pointed at this thing until we understand what it is. If it turns out to be a weird comet, great, we've learned something about cometary physics. If it turns out to be something else, we've made history. Either way, the investigation is justified. The data from dark matter lensing show us that rigorous multi-method approaches work. They turn speculation into knowledge. They transform anomalies into discoveries. Speculation time. If dark matter clumps can hide in plain sight, influencing the motion of galaxies and the path of light without being directly visible, could technological objects do something similar? Not through exotic physics necessarily, but through design. A probe optimized for stealth, emitting minimal radiation, coated in materials that absorb rather than reflect light, would be hard to detect. We'd only spot it if it passed close enough, moved in a way that caught our attention, or reflected sunlight at just the right angle. 3i Atlas is bright, so it's not perfectly stealthy. But brightness alone doesn't tell you what something is made of. A shiny metal surface reflects sunlight efficiently. So does ice. You need spectroscopy to tell the difference. Until we have that data, we're guessing based on morphology and motion, and those guesses keep leading us to uncomfortable places. The dark matter detection reminds us that extraordinary claims sometimes pan out. General relativity sounded insane when Einstein first proposed it. The idea that time slows down near massive objects, that space itself can bend, violated common sense. But the evidence accumulated, and now it's textbook physics. Exoplanets were once speculative. Many astronomers doubted they existed. Then the first one was confirmed in 1992, and now we know of thousands. The universe doesn't care what sounds reasonable to us. It is what it is. Our job is to observe, measure, test, and follow the data wherever they lead. If the data lead to dark matter clumps, we accept it. If the data lead to something even stranger, we need to accept that too. So how do we make sense of all these cases? How do they fit together? Part 14, Synthesis. Lessons from Enceladus, NEO's Dark Matter. 3 stories from 2024. Enceladus's reanalyzed organics. A near-Earth object threading the satellite gap. A dark matter clump revealed by gravitational lensing. On the surface, they're unrelated. Different objects, different methods, different fields of astronomy. But thread them together and patterns emerge. Patterns about how science works, how discoveries happen, and how institutions respond when data challenge expectations. Let's synthesize. Enceladus teaches us that hidden surprises lurk in old data. Cassini flew through the plumes years ago. Instruments recorded measurements, and those measurements sat in archives until someone thought to look again with fresh eyes and better tools. The complex organics were always there. We just didn't see them the first time. The lesson: data have a longer lifespan than the missions that collect them. Every observation is an investment in future discovery. 3i Atlas is generating data right now. Those images, those spectra if we ever get them, will be reanalyzed for decades. Someone in the future might see something we're missing. But that only works if the data are preserved, documented, and made accessible. Open science isn't just an ethical position. It's a practical necessity for maximizing return on investment. The near-Earth object demonstrates rapid transparency and mobilization. Automated surveys detect, algorithms calculate, alerts distribute, observers coordinate. The entire process happens in hours to days. No gatekeeping, no proprietary claims, no waiting for journal publication. The community shares data immediately because the threat is universal and the value of collaboration outweighs the value of secrecy. That model works. It's effective, resilient, and trusted. Why can't we apply the same model to 3i Atlas? Not because it's a threat in the collision sense, but because it's a threat to our understanding. If this object breaks the comet model, we need to know. We need all hands on deck, analyzing every angle, testing every hypothesis. Rapid data sharing would accelerate that process. Dark matter lensing shows that extraordinary claims can be real. The universe hides structures we can't see directly. We detect them through their effects: bent light, strange rotation curves, anomalous gravitational pulls. Those effects were once controversial. People proposed alternative theories to avoid invoking invisible matter, but the evidence kept piling up, and now dark matter is consensus. The lesson: don't dismiss anomalies just because they sound weird. Investigate them. If they persist under scrutiny, adjust your models. The history of science is full of invisible things that turned out to be real. Atoms, bacteria, radio waves, black holes, exoplanets. Each was once fringe or speculative. Each became mainstream when the data demanded it. 3i Atlas is exhibiting persistent anomalies. We owe it to the scientific method to take those anomalies seriously. Thread the lessons together. Science can miss surprises if we don't revisit old data. Science can mobilize rapidly when priorities align and data flow freely. Science can validate extraordinary claims when evidence accumulates. Now apply those lessons to 3i Atlas. We need to revisit the assumptions we've made about what comets should look like. We need to mobilize the global astronomical community with rapid data sharing and coordinated observations. We need to accumulate evidence rigorously, testing every hypothesis until we converge on the truth. That's the path forward. It's not glamorous. It doesn't involve aliens landing on the White House lawn or dramatic press conferences. It's just hard work: observation, analysis, debate, revision. But here's the emotional beat. Trust depends on transparency. When institutions hoard data, when they delay releases, when they speak in jargon that obscures more than it reveals, public trust erodes. People start assuming the worst. They imagine cover-ups, conspiracies, hidden agendas, and once that trust is gone, it's almost impossible to rebuild. The solution is openness. Release the data, explain the uncertainties, invite the public into the process. Yes, that means dealing with speculation and misinterpretation. Yes, that means journalists will write sensational headlines and social media will run wild. But the alternative is worse. The alternative is a science establishment that looks like it has something to hide, even when it doesn't. 3i Atlas is a test case. How we handle this object will set precedents for how we handle future anomalies. Do we retreat into caution and secrecy? Or do we lean into transparency and collaboration? The call is clear. We need an urgent plan for 3i Atlas. First, raw data dumps. Every image, every spectrum, every measurement from every instrument that's pointed at this object. Dump it into public archives with proper metadata and documentation. Let the global community dig in. Second, independent analyses. Encourage researchers at universities, observatories, and institutes worldwide to run their own analyses. Different methods, different assumptions, different perspectives. Cross-checking is how you catch errors and build confidence. Third, coordinated spectroscopy. This is critical. We need high-resolution spectra across multiple wavelengths. Infrared to see ice signatures, optical to see reflected sunlight, ultraviolet to catch gas emissions. Spectroscopy is how you determine composition. It's the key to distinguishing between natural and exotic possibilities. Fourth, open science ethos. Preprint servers for rapid sharing of results. Open access journals to avoid. Paywalls. Public databases for data storage. Community forums for discussion and debate. Make the entire process visible and participatory. That's how you build trust and accelerate discovery. The technology exists. The platforms exist. What's missing is the will to use them fully and the institutional courage to accept the scrutiny that comes with openness. 3i Atlas deserves that effort. The questions it raises are too important to be handled behind closed doors. So what are the stakes if we're right? What are the stakes if we're wrong? Let's talk about both. Part 15. Final frame. Stakes, probabilities, and the responsible alarm. Let's be honest about the probabilities. Most likely 3i Atlas is a comet with weird cometary physics we don't fully understand yet. Maybe it's unusually dust poor. Maybe it's outgassing in a way that minimizes the visible tail. Maybe its shape is naturally elongated due to formation processes or past collisions. Maybe every one of the anomalies has a mundane explanation that we'll figure out once we have complete spectroscopic data and better models. This is the boring answer. It's also the most probable answer. Science is conservative for a reason. Extraordinary claims require extraordinary evidence, and the evidence so far, while intriguing, isn't overwhelming. It's suggestive, it's anomalous, but anomalous doesn't mean impossible to explain naturally. Plausible. 3i Atlas is an interstellar shard, a fragment of something larger, with composition and morphology shaped by processes we don't see in our own solar system. Interstellar space is vast and cold. Objects drifting between stars could have exotic ice mixtures, radiation-processed surfaces, structures sculpted by impacts or tidal forces from close passes around other stars millions of years ago. If this is the second or third confirmed interstellar visitor after Oumuamua and Comet Borisov, we're just starting to build a sample. We don't know what's normal for interstellar objects. Maybe elongated shapes and minimal outgassing are common. Maybe Oumuamua wasn't the weird one. Maybe our solar system comets are the outliers. This explanation is plausible, scientifically respectable, and doesn't require invoking anything beyond known physics, but it does require us to expand our models and expectations. Speculative. 3i Atlas is an alien probe, engineered, launched, sent here deliberately or wandering randomly. This is the least probable explanation. It requires not just that life exists elsewhere, but that intelligent life exists, that it developed technology, that it built spacecraft capable of interstellar travel, and that one of those spacecraft happened to pass through our solar system at a time when we had the tools to detect it. Those are a lot of assumptions, but improbable isn't the same as impossible. The Drake equation, that famous attempt to estimate the number of communicative civilizations in the galaxy, has so many uncertain variables that the answer could be anywhere from one, just us, to millions. If there are millions, then interstellar probes could be common. We just haven't had the sensitivity to detect them until recently. Or maybe we have detected them and misidentified them as comets or asteroids because we weren't looking for the right signatures. Here's the key insight. Unexplained doesn't equal extraterrestrial. That's the logical fallacy we have to avoid. Just because we can't explain something doesn't mean aliens did it. The history of science is full of mysteries that turned out to have natural explanations. Pulsars weren't little green men. Fast radio bursts weren't alien transmissions. Tabby's star probably isn't a Dyson sphere. The universe is full of natural phenomena weirder than we imagined. But ignoring anomalies is also dangerous. If you automatically dismiss anything unusual as measurement error or observer bias, you'll miss genuine discoveries. The balance is difficult. Take anomalies seriously, investigate them rigorously, but don't leap to exotic conclusions without exhausting the mundane ones. That's responsible science. So here's the rhetorical question I want you to sit with. What if Tiago's backyard telescope was the first step in the biggest discovery in human history? What if those pixelated images, posted casually on social media, mark the moment we first detected evidence of another civilization? Not a radio signal from light years away, but a physical object, right here, moving through our solar system, close enough to image? What if ESA's confirmation wasn't just validation of an anomaly, but validation of contact? I'm not saying that's what happened. I'm saying, what if? How would you feel knowing we had that evidence and let it slip through our fingers because institutions were too cautious, too slow, too afraid of looking foolish? History has turning points. Galileo turning his crude telescope toward Jupiter and seeing moons orbiting another planet, proving Earth wasn't the center of everything. That was a turning point. Eddington measuring starlight bending during the eclipse, proving Einstein was right and Newton was incomplete. Turning point. The first exoplanet detection, proving planets around other stars are real. Turning point. Each of these moments required someone to look at ambiguous data and say, this means something. This changes everything, and they were right. The universe turned out to be weirder, bigger, richer than the prevailing models allowed. 3i Atlas could be another one of those moments, or it could be a footnote, a curiosity that gets explained away and forgotten. We don't know yet. But the only way to find out is to investigate with everything we have. Galileo's telescope was, by modern standards, laughably crude. Low magnification, distorted optics, hand-ground lenses that warped the edges of light. But for all its flaws, it was enough. Through that fragile tube of glass, he saw moons circling Jupiter. He saw Saturn's bizarre ears, the rings, though he didn't yet know what they were. He saw Venus changing phases like our own moon. He saw craters and mountains rising from the lunar surface, and with each observation the Earth itself seemed to shrink a little, no longer the unmoving centre of creation. That revolution didn't begin in a billion-dollar observatory. It began with a primitive lens in the hands of someone willing to look. Now jump forward 4 centuries. Tiago, better known as Dobsonian Power, peers through an 8-inch backyard telescope. By the standards of today's space science, Compared to James Webb's golden honeycomb mirrors or ESA's Mars orbiters armed with precision instruments, his rig is primitive, but like Galileo's, it was enough. Enough to capture something that shouldn't look the way it does. An object without a tail, an elongated, alien-like smear in the darkness, a shape that refuses to behave like a normal comet. And here's the twist. When the European Space Agency turned its cameras toward the same visitor, their data confirmed it. The odd morphology wasn't an amateur's mistake, it was real. That moment, an amateur capture overlapping with professional confirmation, is more than coincidence. It's a spark, a disruption, a reminder that paradigm shifts don't always arrive with fanfare and billion-dollar price tags. Sometimes they arrive pixelated, imperfect and undeniable, from a backyard telescope. Warning, coincidences piling up equal time to raise the alarm. We've gone through the list. Weird orbit, weird shape, no tail, independent confirmation, Earth-based and space-based agreement, amateur and professional consensus that something's off. Each coincidence alone is dismissible. Together, they form a pattern that demands explanation. And when the normal explanations keep failing, when every attempt to fit the data into existing models requires increasingly tortured assumptions, you have to consider the possibility that the models are wrong. That's not alarmism, that's science. Models are tools, not truths. When the data don't fit, you revise the model or you build a new one. So here's the call to action. Push for transparency. If you care about this, if you think the questions matter, make noise. Contact your representatives if space agencies are publicly funded in your country. Post on social media, write to journalists. Demand that raw data from 3i Atlas be released immediately and fully. Demand coordinated international observation campaigns. Demand open debate about what this object is and what it means. Science works best when it's open, transparent and accountable. It works worst when it's secretive, slow and defensive. We have the tools to study this object properly. We have the telescopes, the spectrographs, the computational power. What we need is the will to use them and the courage to accept whatever the data tell us. End note. History doesn't wait for institutions. Sometimes it starts in a backyard with someone pointing a telescope at the sky and seeing something that shouldn't be there. Tiago saw it. ESA confirmed it. Now it's up to the rest of us to decide whether we take it seriously or let it fade into obscurity. The images are out there. The anomalies are documented. The questions are asked. What happens next depends on whether we have the courage to pursue answers, even if those answers are uncomfortable, even if they challenge everything we thought we knew. Because the universe doesn't care about our comfort. It is what it is. And 3i Atlas, whatever it turns out to be, is out there right now, moving through space, carrying secrets we haven't unlocked. The only question is whether we'll try. The alarm is sounding. Are you listening?